exam one, right, is supposed to cover these sections. And as I look at, you know, what we've done so far, I, I just want to tell you a little bit about my exams because a lot of you have never had them before. I mentioned to you guys that there will be a take-home exam also. Did I mention this? Okay, so you understand. Because 2 hours, it sometimes takes longer than that to do Calc 3 problems, right? And so, you know, yeah, sometimes you get them done, right? But but what happens is that I'll give you the same exact questions for home, and then as long as you bring me those by next class, you can use your book, you can use your notes, you know. And what I'll do is I'll average your scores, okay? And I do this to really kind of take the pressure off some. This is about learning, okay? And also, like I said, that's how problem solving is really done. The only thing I would ask is I'd ask you guys not to work together on the test, okay? It's not team test. Do your best, you know. And in class I'll have that and here, but as I look at the sections, I notice that some of them aren't really calculus and some of them are. Like for example, today we talked about limits and continuity. Those are calculus ideas, right? 14.1 and 14.2, while I do want you to do that homework, I'm less likely to ask test questions specifically about that, right? I kind of feel like you need to do those quick checks just to get your feet wet with what this whole R3 thing is about, but I wouldn't spend tremendous amounts of time on this, okay? Same thing when I looked at the other sections. You know, 13.5 was on lines and planes and surfaces, but then it was when you got to 13.6, that's when we're now doing calculus. So here we have vector valued functions, but this is the calculus of vector valued functions. So that will be tested. 13.7, we talked about motion in space. So how your velocity is r prime of t, and your acceleration is r double prime of t. And if you take the magnitude, you can get the speed, for instance, right? When we got to 13.8, we talked about length of curves. So we talked about arc length, and then we also talked about, at the end of that chapter, we talked about how to parameterize a curve by arc length. And that becomes important if you want to talk about, well, the important idea in 13.9 was curvature. Right? Curvature, okay. And also normal vectors. So, in terms of your focus, guys, the test will have, and I'm still writing it, either 5 or 6 problems. Well, pages. Okay, so when I say a problem, it's kind of like some of your, I try to make 80% of my test like your homework. So that, you know, for the most part, mostly what you're doing is kind of the same stuff you did on the homework, and that's why that's such an important part of the course. And you think about the homework problems, you know, some of them have parts A, B, C, and D, kind of like I did in class today. Well, I'll do that also. I'll have a page that's testing you on a concept and have a few different exercises. Okay? It's all partial credit. Show your work. Don't leave anything blank. Even if you don't know how to solve a problem, at least show me what you know about the concept because I want to give you points. If it's blank, I can't do that. Okay? I don't like erasing lots of stuff. You could just draw a line through it and move to a back of a page or something like that if you make a mistake or want to restart. So these are all ideas I have for exam 1. Okay. And I thought basically what I would do is go through some problems from each of the sections right now. I thought that might be the best move. So I have a list that we've kind of compiled over the weeks. Some of them we've already talked about, but most of them we haven't. And that's kind of where I thought I'd go. Yeah, this is section 13.6. number 33, a number of people had questions on. They gave me a vector valued function. They said u of t is equal to 2t cubed times vector I plus t squared minus 1 in parentheses times vector j minus 8 vector k. Okay? And they also gave me vector v, but I don't need it for this problem. Problem 33 asks me to find u of no, it asks me to find the derivative. Okay, so it says find the derivative of u of t to the fourth minus 2t. That's what the problem says. Okay. So my Calc 1 idea that's coming back here, any guesses?
Either product rule, or you could just distribute it beforehand.
So that's interesting. I mean, does this mean u times t to the fourth minus 2t? Or does it mean, what does it mean? So you're thinking chain rule because it means u of t to the fourth minus 2t. And that's an important distinction to make, right? As a matter of fact, as I look at those exercises, I think that is one of the points. Look at problem 31, which was not assigned. Can you see it? Is it big enough for you? Zoom in a little bit. 31, to me, is a product rule. Same with 32. But things like 33 and 34, those are chain rules, okay? We might have done 35 or 36 in class that day. That's a product rule using a dot product or a cross product, okay? So yeah, I'm thinking, I better zoom back out, but I'm also thinking chain rule is what's involved here, right? Which is cool. We're going to come back to the chain rule again next week? Maybe, yeah, might be next week. Maybe the week after. So I won't say too much, but I'm going to say that I'm taking the derivative with respect to what? T, I agree. It's kind of like we used to do d dx quite often in Calc 1, right? So d dt of u of t to the fourth minus 2t is going to equal u prime of t to the fourth minus 2t times the derivative of t to the fourth minus 2t. That's the chain rule, is that dong. My Calc 1 students, it's like we do ding, dong, right? You have to take the derivative of what's inside. And so, I guess what I'm going to do is I'm going to do a couple of computations. I'm going to compute, my steps are going to be, I'm going to compute u prime of t. Then I'm going to tell you what u prime of t to the fourth minus 2t is. And then for my final answer, I'm going to take whatever I had and I'm going to multiply by, it looks like 4t cubed minus 2, right? Because that's the derivative of this function. Make sense? All right, let's see.
Is it also okay to plug in that chunk into where t is in the original function?
I wouldn't do that.
No.
Can you? Sure, you can. Let's go back to Calc 1 for a second, guys. Suppose I said, find the derivative d dx of, you know, x squared plus 2 to the 27th power. Now, this is a pretty easy problem using the chain rule. 27 times x squared plus 2 to the 26th times 2x. Do I have to do it that way? No. I could take x squared plus 2 and multiply it by itself 27 times and just use the easy way. Don't do that. Right? So there's a reason. Yeah, this is a chain rule problem. Let's do it the chain rule way. So here we go. U prime of t would be, and if you guys are okay with it, I want to switch to the bracket notation. I just think it's faster, and we're on the clock. So I'm getting 6t squared. I'm getting 2t, and I'm getting 0. Yeah? And so next, when I take u prime of t to the 4th minus 2t, what that means is everywhere there used to be a t, you're going to write t to the 4th minus 2t, right? T to the 4th minus 2t, and then 0. And so then, I guess what I need to do is just multiply that by this. Yeah? And I guess the question is, do you need me to do any more, or is that good enough? It's good enough for me. So, problem 50 was the baseball problem. We had the picture of this on, you can still get to, I think, if you go to our Blackboard page. It was the first time we used the GeoGebra. And so the question was, well, when does the maximum height occur? And actually we could see it, right? It occurs right here, right? So we had expressions for r of t right here, and we computed an expression for v of t right here, right? Right, so the question is, when does the maximum height of the ball occur? And they say, well, it's when negative 32t plus 80 equals 0. So where did they get that from? Okay. It looks to me like what this is the z coordinate of the velocity, right? Mm-hmm. And so what they're saying is, look, the ball is going up. That's a positive velocity, right? It's at a maximum when v of t is 0, right?
First derivative equals 0.
Yeah. Matter of fact, that's an even better way to think of it, because r prime of t equals 0. That's how you find maxes. So that's what they did. What's cool about that, too, is that that works no matter what shape. There's actually other things you could do because it's a parabola. I could say, well, I know because of symmetry, it's halfway between here and here. No, but this is what we learned in Calc 1, and we're going to use that idea again. That's a good question. Okay. Yeah, but I thought that you guys were doing pretty well with the 13.7 stuff overall, from what I've seen. Anything else before I go to 13.8? 13.8, I wrote down question 43. Let's see what that's all about. Yeah, so then what to say about arc length? Well, you need to know, right? How do you get the arc length? Well, what's the basic formula? You want to integrate what? The speed.
Is that different from the magnitude of the position?
It's different.
Yeah.
Yeah, it is different. Right? Why is it different? Because we're in higher dimensions. So because these are vector valued functions where I have 3 coordinates. And so, I mean, how do you get magnitude, right?
Will the magnitude of position just give you the distance between the starting point and the end point
That's
in
right.
a straight line?
That's right. It's straight line distance. Yeah. But we don't want straight line distance. We want distance along the curve. And so what you're really doing, okay, this is, you know, here's the picture, right? We want the arc length. So we're going to do this, guys. We're going to draw a straight line length. That's what you just said. And then we say, well, wait a minute. We're going to want a better approximation than that, because if I add those two lengths together, that's not the arc length. That's a far short. So I'll increase n. I'll say, well, okay, right? Now I'm closer to the arc length. Those straight lines I could compute. If I increase k, oh, this is just where I am right now, right? But what you want to do is you want to add all those together. And guess what kind of sum you get? You get what's called a Riemann sum. And when you take the limit as these deltas go to 0 of the Riemann sum, that's an integral. So that's really where it comes from. Okay. Yeah, so maybe we move on. So, yeah. It says, this is problem 70. Did I assign this one or no? All right. I want to talk about it for a second. It's called the osculating circle at a point P. This is actually another way of thinking of curvature. So suppose you have a circle in the plane and you want to compute the curvature, right? And so let me go ahead and do that. Well, let's take a circle. My example is, suppose I have a circle of radius A, let's say. A circle of radius A. Now, how do I define this circle in the plane? Well, yeah, x squared plus y squared equals r squared is great, or a squared it would be, right? But I'm trying to do vector calculus with you guys. So do you know how to define a circle in the plane? What's that? Cosine and sine, yeah. So if I do this, guys, if I say x of t is a cosine t, right? And y of t is a times the sine of t. You guys know enough trig to know that that's going to give me a circle of radius a? Yeah? If you don't believe it, what's x squared plus y squared? Well, what's cosine squared plus sine squared is 1, so x squared plus y squared would be a squared. And you're probably happy at that point. Okay? So if I have this, then to do vector calculus, I can just say my vector is the vector x of t, y of t, right? And then you guys know what to do. You know how, at this point, you know how to take derivatives, etc. So, you know, if I want to compute r prime, what I'm really interested in, I guess, is just x prime and y prime. So that would be, you know, negative a sine of t, and this would be a cosine t, and then I have x double prime would be negative a cosine t, and y double prime would be negative a sine of t, right? And now, if we want to compute curvature of a curve in the plane, let's go back to the book for a second. Because you guys have a lot of formulas for curvature at this point. Here's a special formula, right? But we have this one, 55. And I think this is really what you had to use here. So there's the formula. I'm going to write it down, and then we'll use it. Okay? So, in particular, for me, okay, when I come over here to write the curvature formula, I guess I'll do this. I'll say k is this big fraction, and the denominator of the big fraction is to the 3/2 power. Okay. And I guess the numerator has absolute values. Okay. And it's just that instead of f's and g's, what do we have? We have x's and y's, right? So it's f prime g double prime, right? So for us, that would be x prime y double prime. All right, so here I go. X prime y double prime minus x double prime y prime over f prime squared plus g prime squared. So for us, that's x prime squared plus y prime squared, right? So there's the curvature formula that I want to use. So let's see if I can do it. Okay. Well, curvature would be bigger fraction. So let's see, we're going to take negative a sine of t squared. Oh no, that's the denominator. Well, do you see where I got that? That's the numerator. If I take x prime y double prime, see how it matches up? So that's where I wrote the squared. Minus, and now x double prime times y prime, I guess we get what? Negative a squared cosine squared t. Is this okay? How's my pace, guys? Am I okay or too fast? Okay. And then stuff to the 3/2 power, so let's see. We need to square x prime and we need to square, right? So we're going to take this negative a sine t and square it. And we're going to add what we get when we take a cosine t and square it. So, what do we get? Let's see. Well, this negative a was being squared, so that's going to give me a squared sine squared t plus, because the negative negative, a squared cosine squared t. That's really nice. All over. And then down here, this one works out nice too, right? Yeah, you get a squared sine squared t plus a squared cosine squared t, right? So this is beautiful. We get a squared over a squared to what power? Well, it was 3/2, right? So now I just need my laws of exponents. What? Yeah, Matthew? Okay. So the next step would be a squared. What do I do with these exponents when you have a power of a power? Multiply them. So this is a cubed, right? And so what I just showed you guys is that the curvature is equal to 1 over a for a circle in the plane. All right? Well, if you understand that, then you understand something really cool, which is this. When we say we're going to compute curvature at a point P, right? And I'm not saying this is a circle, guys. This might be part of a helix or what other curves have we seen? Roller coaster, right? I want to say, how curvy is it here? Well, first, do you understand that I can draw circles that are tangent at point P? Do you know how many, though? There's actually infinitely many circles. You could have a little one. You could have a medium-sized one, etc., right? Only one of them has the same curvature as the curve. Because we learned that curvature of circles gets bigger or smaller, right? And actually what you want, okay, so there is a unique circle, okay? The osculating circle, or the curvature, circle of curvature, the osculating circle is the circle with radius 1 over the curvature. That's the deal. If you made A equal to 1 over the curvature, then the curvature of the osculating circle would be the same as the curvature of the green curve we started with. That's kind of what the calculation we just did shows you. And it turns out that actually if you have a curve and you define 3 points on the curve, there's a unique circle passing through these 3 points. 2 points, that defines a line, but 3 points would define your circle. Well, what you do then is you say, imagine those points all got pushed to point P. Then you'd have what's called second order contact, and that's what the osculating circle is. So these problems here in the 70s about these circles are talking about this. So let me go back to that 70s problem and see if I have a hint. Oh, find the radii of curvature. So basically, you guys had 73, for example? Basically, all you need to do, right, now that you've seen that, here, let's punch this back up. Just find the curvature, take the reciprocal, and that has to be, from our calculation, the radius of the oscillating circle. Is that enough of a hint? Hopefully. What else? People asked about 77 and 81 also, but I think those are different. Oh yeah, use technology. Find and graph the speed. Find and graph the curvature. At what times do the speed and curve... Oh, that's why I assigned this one. Where does the curvature have a maximum or a minimum value? Remember I showed you guys that research that was done? That's why I assigned that one. Yeah. So it's interesting. I talked to you guys about the test. I said 80% of it will be like your homework problems. Okay? That means there's an extra 20%. 20% is what I like to call my stretch questions. Okay? This is a stretch question in a way. It's going to make you work. Okay? So do understand there will be some questions that stretch you. And we'll see what you can do in those 2 hours. But you have the take-home test too. Okay? So do understand there's going to be both on the test. 81. Yeah, maximum curvature. Again, I saw this is so related. I said let's find the curvature function Fn for n equals 1, 2. Maybe you need help just with that. 81a. I only have 1 minute. I don't know. Maybe it's time to hang it up, guys.